Hello.
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 Hello. All right. So I think everyone is more or less here. We can start. Last time actually we started with the droplets formation, but we did not finish it. So I'll continue with that. But then I realized actually there's one thing which we still need to go back with to the Kolmogorov turbulence, because I forgot to discuss with you the Kolmogorov microscale. So this is not a very difficult concept after we have more or less managed with the Kolmogorov turbulence in itself, but still if we go through topics which are important in the context of turbulence, so knowing what is the Kolmogorov microscale is important thing, definitely. So we definitely need to discuss that. Now let me again share my screen and let us start going then. Which one of those two? I think it's more or less the same. All right. So what we had last time was that you concluded that droplets start growing diffusively, and only later on they start moving related to each other and start colliding, and so you will be having rain. And now, how does the diffusive growth happen? So we have now a droplet, and let us say it has a very small radius and moves together with the ear mass. So around it, we have a certain supersaturation. So because it is in a cloud and it goes up and it goes down, dew points goes temperature falls below the dew points. So relative humidity is a pressure of vapors divided by the pressure of saturation vapors. And now, because saturation pressure goes down, the pressure of vapors also changes, because it's like adiabatic, but it will change much slower than the saturation pressure of the vapors. So it's mostly a value of relative humidity is divided mostly by the saturation pressure. And so it goes something like, let us say, maybe 1.02 or something like that. Who knows? But the main thing is it's more than one. It is oversaturated. And if it is oversaturated, so this you probably know, oversaturated doesn't necessarily mean that it starts immediately condensation, because it can go only into liquid phase. So you need to have a liquid interface somewhere. So what is, probably you guys know what is saturation pressure, just in case, let me repeat. So saturation pressure means that we have liquid gas interface. Here is a liquid phase, and here is the gas phase. And inside the gas, you have a vapor also, like this liquid in gaseous state. And now you have two processes. One process is molecules from the liquid jumping out because of random gain of energy. So you know that the Boltzmann distribution probability is on the order of E are proportional to E minus, and then exit poek U divided by K BT. So Boltzmann distribution again. And this process actually, well, you can obtain this thing in different ways. There is also this way of obtaining it. Now how it's called, cannot say immediately. Oh, never mind, it's not that important. And so the rate at which they jump up is proportional all to the probability of gaining energy U. So you can see that if temperature goes up, exponent goes smaller and probability will grow. So if T grows, P also will grow, probability of jumping up. So this probability is not to confuse with the pressure. So actually the symbols are not very successful, but I cannot figure out that symbol for probability as well. I can make it capital P capital maybe making it different from the pressure, which is P small. Yeah, what I forgot to is the name Clausius-Clapeyron. So actually, these things, the probability of jumping up or saturation pressure is proportional to this exponent, and you can derive it also from the ideal gas law together with the Carnot cycle and entropy conservation as Clausius-Clapeyron law. So two different ways, either starting from the Boltzmann distribution or Clausius-Clapeyron. Either way, you have this dependent for the probability and also for the saturation. But then we have another process, which is vapor molecules from the gas colliding with the liquid. And now this probability here is frequency of collision is proportional to the density of vapors here. So if you have a density, a number per volume is n, so well the frequency f with which they collide is equal to the density multiplied by speed. So this is a particle flux. The frequency per unit area. So in order to have total number of collisions per unit area A, you multiply the particle flux n times v with the surface area, and this is the collisions from gas with area A. And V actually here is basically the thermal speed, which is square root of kb T divided by n. And so you can see that frequency goes up if density goes up, if the number density goes up. And now saturation pressure is when these two processes are in equilibrium. If there are as many particles colliding, because once it collides, it can get stuck, and most likely will get stuck. And so if the two processes are in equilibrium, we have same process going at the same speed, we have thermodynamic equilibrium. If pressure equals to, if the vapor pressure equals to saturation pressure. Now, if the pressure is smaller than that saturation pressure, then more particles jump up, and so liquid starts flying up. And on the other hand, if it is the other way around, then we have condensation here on the liquid. But this is valid only if we do have a liquid interface. If we don't have liquid interface, then particles have nowhere to collide with. And so you will not have condensation, even though you have pressure of vapors bigger than saturation pressure. So relative humidity more than 100%. And so in order to have condensation, you need to have condensation centers. So how condensation starts, then you have a tiny dust particle, water molecule goes here and gets stuck. And then you will start having a liquid water air interface, and it can start growing. So and that's why you have in the gas, you can have relative humidity more than 100%. That you just don't have enough condensation centers. This is called as as oversaturated papers. And now let us take new page, because I think here is too small area left. So now what happens around now that droplet here? Around we have P, let us denote infinity, separation density and far away. And then on the surface here we have on top of that surface we have and at the immediate contact we have equilibrium. As many particles as go up from the liquid, as many will condensate on the surface. So here we have a P equals P saturation. Pressure of vapors equals to saturation pressure. And now we have like a quasi-equilibrium here from the droplet to the surrounding. And now we need to write down now a diffusion equation. So we have a certain diffusion coefficient, and particle. So for the concentration of particles, let us say N. Concentration of water molecules. We have equation G and maybe let's start with the particle flux J equals N multiplied by diffusion coefficient D multiplied by gradient of N. D gradient of N. This is a particle flux. And then we have
no advection then.
Sorry?
No advection.
No advection. Because why no advection? Because the particle is just moving together with the fluid. And in the frame of reference where fluid is, well, there is certain strain which might become perhaps important, but not that important for the time being. So we neglect that strain, and because we are in a co-moving frame and look at the very small scale, and our scales are small because we need to consider just from the area, the immediate area surrounding the small tiny droplet. So it is really a very small area, and related speed is, will remain small. And so J is D gradient of N, and then we have because we have very small scale, the characteristic time at which things change, tau, characteristic tau, time tau is estimated as scale like A squared divided by D. But because we are speaking about very small characteristic scales A, so tau is very small. Very small. So because of that, we can say that it is quasi-equilibrium. We have dN over dt, which is d Laplace of n, but this is approximately 0. So we need to solve Laplace equation. And now a Laplace equation in 3D, you know the solution, right? So what might be the solution for Laplace equation in 3D? Okay, then. In this spherical symmetrical case, we have spherical symmetrical case. We have like the same thing is for. I wrote here for pressure, but because pressure and concentration are directly related to each other, we know that the P is NKT, and because we have thermal equilibrium, assume that everywhere T is the same, and so P is directly proportional to N. So if we have equation for N, we have also for P, and the other way around. And so the boundary condition for this problem is that we have certain value maintained for density at infinity, and we have certain value maintained here at the surface. Saturation value at the surface and something slightly bigger at infinity.
There was not a logarithmic term in the solution of Laplace equation for that.
No logarithm. No logarithm. In 2D, in 3D. In 3D, no logarithm.
But in 2D, yes.
In 2D, yes. In 2D, yes, but not in 3D. You might easily figure out if I write another equation for you. So we have now another equation which states Laplacian of phi equals minus rho divided by epsilon naught. Is this familiar to you? Does it remind you something, this equation?
Yeah. Oh, it's the
electric
first,
potential, yeah.
yeah, the
Electric
first
potential and its spherical symmetrical case. What is the solution here if we have 3D space? What is the solution for phi?
like the solution in terms of field.
Yeah, so we have point charge potential.
The equation
In 3D, like point Coulomb law.
E
Coulomb,
equal to divided
Yeah,
square.
so phi equals phi at infinity. And then which way now minus the plus. We need to figure out, doesn't matter really, depending on in our case. So we have a potential goes up, so plus and plus total charge Q divided by 4 pi epsilon naught and R, things like that. That factor Q, I'm not sure, Q divided by 4 pi epsilon naught. I'm not sure how important this is in our case, but what is important that we have term which is inversely proportional to distance. So I can say also here for the previous equation, for that here we have n equals certain n at infinity, and then now minus, just we need to match boundary conditions now. We know that we have the solution comes in two parts constant, because constant definitely satisfies Laplace equation. And the other is this 1 divided by R term, which is also satisfies, and because I have linear equations, and any linear combination of those two also satisfies. So we basically can take any arbitrary constant here for the second term and divide it by R. And we take some delta n, which is the concentration difference. And now we have Laplacian and delta too similar. Maybe we make it the other is small ring delta, and delta n divided by R. R is the distance from the center of the droplet. And here we have expressions for how now a concentration depends on the distance from the center of the droplet. If we have quasi-equilibrium, and we expect to have quasi-equilibrium because the characteristic time scale is very small. But now that is not so much what we are looking for. We are looking for how fast the droplet grows. And now, so basically, we need to calculate integral of J, the flux, dA. That's what we're looking for. How much water molecules will go to the droplet. And then J now becomes, let me now try writing it down, because we have the spherical symmetric case. So we just multiply total here, which is 4 pi R square. We multiply this with J, and J is a gradient of this guy over here is dn divided by R squared, and multiplied by diffusivity d. And then we can see that R squared cancels out as it should, because we have the same flux everywhere going towards the droplet, and we have 4 pi T and delta n. And so this is the particle flux on the one hand. And now let us introduce a droplet radius, R capital. R capital is droplet radius, and then this thing here is going to be equal to the change of the droplet volume, and this is now 4 pi r capital squared multiplied by dr. Oh, no, wait, did I start writing here? dr over dt is the right. So flux is per unit time divided by dt. And now I think we missed something. So this is number of molecules. What we have here is a number of molecules, what the molecules go into the droplet. Now, we need this to relate to the volume change. Here, on the right-hand side is volume change rate. So, in order to get this going to the number of molecules, we need to multiply by the number density in the liquid phase. Number density of particles in liquid phase needs to go here. N sub L. And now I think we have things mentioned. This thing here now, we need to try to find how the radius R capital will start depending on time, how the growth happens. So we can let us rewrite it now, this thing here, in such a way that 4 pi cancels away. We have n liquid 4 pi r squared dr. Let me write down, but actually there is one thing I'm not very satisfied with. Let me check if there are any mistakes or not. Then I just write it down. NL4 goes away, sorry. 4 goes away, NL r squared dr equals dn, and dn is the concentration difference at the infinity and at the droplet. So it is like it describes oversaturation, how oversaturated it is. dn and multiplied by dt, and then we would be able to integrate this to obtain how it becomes basically r cubed, how it will change in time. But now let me see. Actually, I don't like 100% what I have, because I think I should have r squared growing as integral of the oversaturation dn. But now I'm going to have r cube as going. Let me see if we have been missing something over here. That's far. So everything clear? What I have been speaking more or less?
Not really, like the part on the 3D solution of the Laplace equation related with electric field. Like that part was speaking very fast. And
we can discuss it in more detail if you like.
Not detail, like just a very summary, but slower.
Right. So we have analogy between the concentration of molecules over saturation here and the Laplace equation for electrostatic in the electrostatic case. Both are expressed as Laplacian of n equals 0 or Laplacian of phi equals 0 if we have no charge. So actually, this goes to Dirac delta function divided by epsilon naught in the case if we have a point charge. So it is 0 apart from the point where we have the point charge. The same way as so in both cases we are looking for spherical symmetric solution. And so we do know this already. Of course, we don't go through it and derive it once again. But as a mathematical exercise, that would be fine too. But on the other hand, we can just apply what we already know, because from electrodynamics we know that this is the solution in 3D case. And so now, if we look here, we can see that there are two solutions. Like we know that because this is differential equation of linear differential equation of second order, we expect to have two linearly independent solutions. One is this a constant term here, and the other is 1 divided by r term over that. So this Laplacian of that is 0 because any derivative is constant is 0. But here also the Laplacian is 0 because what is Laplacian? Laplacian is
sorry, the analogy is that if I make a charge appear instantly in an empty space, then the electric field starts propagating in that way. And if I make appear a Dirac delta of concentration of some dye, some tracer in a point, it will expand in the time with the same law, with same law with some coefficients different. That's the thing.
Yeah, the thing is that maybe let me write down the solution now. For this equation here, I did not write our equation for the equation for n. So if I take this one here, and now let me write here a solution of that guy over here. So using this analogy here, we can write down solution in the form that n equals certain n which is constant, let us call this n at infinity, plus a certain integration factor c divided by r, because I know we apply exactly the same form as here.
So in the analogy, like the diffusion constant of the electric field is the speed of light, right?
No, because we don't have here
like the speed
of electric field. We don't have actually a diffusivity here. We could have in certain cases diffusion equation also for magnetic field, but in that case the diffusion coefficient actually depends on the resistivity. So speed of light, in this case, if speed of light goes, if you have wave equations, there goes the speed of light. But what is equation? Let me write in the next page. So if we speak about the electric field, we have something like that: d square phi over dt square equals the Laplacian of psi. And now let us make dimensionalities fitting. So we would need to put here c square 1 divided by c square, and that will do it. So you can see that if this is 0, then we have Laplacian of phi equal to 0. So this is no diffusion equation. This is no diffusion coefficient, because diffusion equation would be, and I can write now honestly, this is magnetic field, something like that: dB over dt equals certain diffusion coefficient and Laplacian of b, for instance. Here we have diffusion coefficient. So as you can see, C is no diffusion coefficient. But we are looking at this stationary case, and that's why we have Laplacian of phi either way 0. So even so, the Laplace equation does not come in this case from the diffusion equation, but instead it comes from wave equation. But the end result is the same. Laplacian is 0, and that's what matters right now. All right.
So sorry, just to summarize: electric field goes with wave equation, and magnetic field with diffusion equation.
almost, let us say, magnetic field can go as diffusion equation if you consider a resistive medium. If you consider how magnetic field evolves in resistive medium for processes which are slower, propagate at slower speed than the speed of light, then it becomes diffusion equation. On the other hand, if you consider processes which happen near the speed of light, then you have also that the same second derivative as well, which corresponds to the wave equation. So it depends which case you consider.
With zero resistance, the magnetic field doesn't diffuse, but
yeah, in that case, magnetic field will also describe by wave equation. If you like to be precise. On the other hand, if you consider processes which are slow, then you can neglect the time derivative which goes away. And if you add resistivity, then you will add first derivative, and then you have diffusion equation.
Okay. So why, like for magnetic field, we have this two-way happening, and for the electric field we have only the first? Like, doesn't it exist a resistance for the electric field? Like basically epsilon zero can be, like there was a formula like epsilon equal to epsilon zero times a factor that linearized it, for example, and then also the electric field becomes a diffusion or not, or becomes something else. I don't know, like transport.
Yeah, well, there is no symmetry, no strict symmetry, because between electric and magnetic field, the reason being that you don't have magnetic charge, you have only electric charges. That's the reason. And so what is giving rise to diffusion equation for magnetic field is moving electric charges. And because you don't have moving magnetic charges, so you won't be having a diffusion equation for electric field. This is where it comes. Okay. And now, yeah, with all that, we have still, I have a little doubts if my expression here is 100% correct, because as I said, I was expecting R squared, the surface area growing proportionally with time. Well, it is not that important if we have square or cube over here in general, but just it would be better to have everything correct. So please try checking what I have here. These things over here. If you can point some logical mistake overlooking over here. If not, then we just go on, and even if there is a mistake, we continue. But let us try first if we have something to fix over there. Particle flux is concentration gradient. Concentration gradient is dn over r square. Concentration, if we multiply 4 pi r square, we have quantity which depends only, does not depend on the radius, and then the honestly, I cannot pinpoint here mistake. What about you? Anyone? Artur, how are you feeling? I haven't asked you so far.
I'm okay with it until the step with where you say 4 pi d delta n is NL 4 pi r squared dr dt. I don't see where that's coming from at the moment.
Oh, okay. So where is this? You're asking where this term comes from, right?
Yes.
Okay. So we have from the right hand side here is particle flux multiplied by flux density multiplied by surface area and summing over. So this gives us how many particles arrive at the droplet. So a number of particles per unit time. If we multiply flux density per surface area, we obtain how many particles per unit time arrives at. Now we say that all those particles which arrive will get stuck to the droplet, which means that the droplet will become now bigger. Volume will grow. So if volume grows, the surface area multiplied by the increment of the radius. So 4 pi r dr is the change of the volume. But we want to have number of particles, so we multiply this by the number density of molecules in liquid phase. And then it should give us a number of particles which got stuck to the droplet, so the droplet got bigger. And all this is per unit time, so divide it by 50. Is it okay?
Yes, that's clear.
All right. Yeah, let us just continue. Maybe I can again think later on. By usually when I have some mistake, I try to fix this in the summary, which I send you later. So I have been always doing that way. So the things which I have mistakes, I fix it later. So let us continue. And then from this equation over here, we obtain something like that. For volume of droplet times NL will grow as integral d concentration difference, which is oversaturation basically, dt. So this is a proportion to the integral of oversaturation along the trajectory of the droplet. So how big a droplet is depends which regions in space it goes through. Let me write it now here. And again, my mistake is that actually I know this. It should be actually not volume grows as the integral, which should be surface area r square growing as this integral, and it seems I have missing or overlooking some radius factor over there, but right now I cannot figure out where and how.
Excuse me, I can't understand the V and the predicts are L.
Volume of the droplet radius cube multiplied by number density n sub L. N sub L is the number density of molecules in liquid phase.
So it's NL.
N sub L, yeah. Number density in liquid phase. L stands for liquid. N and index is L. Let me write it better. Let me write it like that. 4 pi r cubed over 3 multiplied by n sub L. Okay?
Okay.
Yeah. And so I say that volume is proportional to integral of P pressure minus P at infinity minus P saturation and integral of dt. So integral of oversaturation over the trajectory of the particle. And now the thing is that because of that, you will be having bigger droplets at the higher parts of the cloud. Well, it's clear that actually if we go upwards with the cloud, then the oversaturation becomes bigger. And so in upper clouds, about parts of the cloud, actually this integral is bigger. In the bottom parts of its integral is smaller, so we expect to have bigger particles at top and smaller particles at the bottom. And but in the same neighborhood, you expect to have more or less the same size particles. And this means that actually they still cannot collide, because how they would be able to collide, I think this I also explained last time, that if we have now, suppose we have a volume of here, and we have here some small particles, suppose now we have some small here droplets and some big droplets. They are, let's assume they are still both very small, so that they have inertia small, so it move together with the fluid. But this, I think, here actually moves with a really big acceleration, so that this probably dominates even over the free fall acceleration. So acceleration of the partial force of inertia is bigger than the gravity. And so now gravity force applies, inertia force is applied here. Here, a force of inertia, and force of inertia is also here, phi prime. And now, if we have big and small ones, then let us make here also small one. So this will be slightly start shifting because of the force of inertia related to the air molecules. And big one has bigger force of inertia, bigger speed, because Stokes law grows only linearly with radius, force of inertia grows as q, and so it's more related to small one and can collide and can eat small one. And so the first thing how the bearing is initiated is the growth of the spectrum of droplets. So they start with, if you take here spectrum, number and radius. And then you start with all having more or less the same radius in the same region, like a small parcel of here, and then all the water molecules in that parcel have all the water droplets have the same size, and they move together, and force of inertia kind of brings them together. But then again, later on, the spectrum will start widening, and then the larger ones will collide with smaller ones. And this will initiate now the growth of much faster growth of the size of droplet, faster than the diffusion current growth. Now, what can give rise to the different growth of the droplet radius? One possibility is to have like a different, one explanation for this can be that we have different droplets having a slightly different histories, and some, like in the same way as you have in the fully developed turbulence, you remember that we had mature fronts. We have here cold, here is hot, and here we have like a big drop. Here we can also have like into the same volume come particles which went up, come here, and particles which went down and come here. And now those which went up and come here are bigger than those which went down and come here. So if can bring together in the same region particles with different histories, which have been in bigger oversaturation areas and in smaller oversaturation areas, now we have a spectrum growth over that, or droplet size growth over that. This is one possibility which can accelerate the initiation of rain. Now, another explanation actually comes down to that intermittency thing, which I explained last time. So all the estimates which say that factor of 10 is missing are based on a simple like a Kolmogorov scale with no intermittency. But then again, if you have some very small, very violent vortices, then they say that you can have a so-called sling effect, which means that we have a very small, very violent vortex. Sling, so-called sling effect. And for that thing, you can look into Falkovich et al. 3 authors, I think. Et al. And it is in Nature, a Nature paper, which they propose that sling effect thing. That we have very small vortex due to intermittency. Usually, the vortexes have that same Kolmogorov microscale, which what I'm still going to explain you. But then you have some very violent one, much stronger than usually because of intermittency. And then you have here a droplet which is thrown out from the sling, like when it goes out from this violent vortex, it will move relatively now, like in the sling, like you know what sling, right? You have like a rope and then a stone fixed here, and then you like rope,
okay.
and
Yeah.
and then you make it rotating, and then you release it. It's all the same thing, like it rotates here in the violent vortex, and then it releases and goes out.
So like basically it's the centrifugal force that breaks the potential.
Well, not exactly centrifugal. You keep it basically like the rope keeps in circular motion, and then if you release it, it goes correctly. So if you release it, it goes with the same speed which it goes.
So the releasing is when the particle goes out, the drop, it continues.
Yeah, if it goes out of the vortex and there is a base, like that's it. And then it goes out, and then it can collide with those molecules which were outside. Now you release it, and it has still its inertia, even though the inertia is small, so it is droplet is small, force of inertia is small, but still because it went out with very big speed, it will still continue going to follow liquid. And if during that little bit going, it will manage to collide with another standing small droplet over there, then will merge. And if they merge, then this will already initiate the process. Now it is bigger, and then it just goes continue. Yeah, it would be good also to look into the numbers, but we are speaking still about scales which are around millimeter or smaller. So all these small bodies are actually very small. And now I think I've more or less covered what was expected to be from the rain initiation. So more or less clear what is going on with the rain initiation. So just things to keep in mind that there is so-called bottleneck problem, and there are different explanations. The most famous one being the Falkovich one, the sling effect. And there is still seemingly some mismatch between the estimates, and there are still like ongoing research in this regard. And also, actually, why the problem is like so difficult to handle is basically because it's very difficult to reproduce things in laboratory. Whichever way you look, is it sling effect or like having particles coming from very different regions of space. In both cases, you need to have large areas, very big Reynolds numbers, which gives rise to very small Kolmogorov microscale, and they are almost impossible reproduce in the laboratories. So what you can, the best you can do is like just send some airplanes to the clouds and trying to take like parcels of air from there and looking at the distribution of the droplets. So actually the key experiments, what we need to consider to understand it, like is first thing is understanding that droplet size distribution. So an important part of this rain initiation thing is how the droplet size spectrum will grow. It starts with almost all the droplets being the same size because they have come from the same space with the same amount of saturation, but as time goes on, they start growing. And then you have to understand, experimentally, you need to study those droplet size spectra and compare those with theory predictions. So this is like a very important step, that droplet size spectrum. Now, Moolas. Artur, Moolas here. Kaido. Now, then let us go on. The next thing, what I said, as I told, I forgot to tell you, is the Kolmogorov microscale. So when I spoke about Kolmogorov turbulence, what we learned was that velocity associated with certain scale r is proportional to r to the power of 1/3. That's what we learned. Now, but and then what we say is that this happens in the so-called inertial range from the input scale. Input scale to the dissipation scale, or Kolmogorov microscale. Let us denote it like maybe eta. And then Kolmogorov microscale. And then you have like this power law here. If we have log axis, so this is a log, so log, and here also log of t. Then it's straight line. And this is inertial range. Just about the terminology. But now the question is, how is this thing here? What is the value of this thing here? Is the question. And now usually it's expressed in terms of viscous energy dissipation, epsilon. I already used that epsilon. You remember for the Kolmogorov for fifth law. There was something like that. R cubed is proportional to 4 is equal to r d over dr cubed over the distance between two particles in the fluid will be epsilon 4/5 epsilon and that's it. Yeah. So r cubed will grow as no, sorry, all wrong. It was something like V, third order structure function, VR cubed, average, it goes as 4/5 epsilon like that. So that epsilon, which is energy dissipation per volume, energy dissipation rate. So we can say it like watts per cubic meter. Anyways.
Sorry, what is the axis?
Sorry?
The Kolmogorov microscale, it's meter?
Yeah, it's on the order, it appears to be around on the order of millimeter in the case of atmospheric turbulence. Depending on how strong the atmospheric turbulence is, it can be smaller or bigger than millimeter, let us say from 1 centimeter maybe to 1/10 of millimeter maybe. but on the order of millimeter. In the case of atmospheric turbulence, he was speaking laboratory experiments. Since this is another story, but for air and for atmosphere, it's around millimeter. But we are yet to obtain expressions for it. Now, and what we're going to do is we are going to express this in terms of that energy dissipation rate. So again, what happens is that we have certain energy input at large scale, like sun heating and putting in the motion, and all this energy input goes all down to cascade to smaller and smaller vortices until it reaches the dissipation scale when the kinetic energy of the fluid goes into dissipation, into heat. And of course, because of energy conservation law, actually that energy dissipation rate is also equal to the energy supply. So as much we supply, as much needs to dissipate at the end of the day, right? So energy dissipation rate also equal to energy input rate, of course. But usually we speak about not that energy as an energy input rate, but as energy dissipation rate. Also, those two things are the same. And now, let us recall how we derive the Kolmogorov turbulence. So we wrote energy transfer, and that thing was kinetic energy. We are now a square and multiplied by tau r, characteristic time related to these vortices. And tau r was equal to VR divided by R divided by VR, so it becomes VR cubed divided by R. That's what it was. And then this is how much energy per unit time is transferred from bigger vortices to smaller vortices. And once it reaches the smallest vortice, it goes to dissipation. So that's the same guy actually is epsilon. And now epsilon is not per volume, but per kilogram, actually. Maybe it's easier for us to write not per cubic meter, but per kilogram. Then we get rid of that row over there per kilogram of here. And now we are cubed divided by R is epsilon, dissipation rate, and this is our first equation. And the second equation is going to be, and now we are going to relate the dissipation rate, the viscous dissipation rate. And so this is from the Navier-Stokes, actually, we can obtain a result that dissipation, viscous dissipation is basically gradient, velocity gradient squared and multiplied by the viscosity. And now at the smallest scale, that gradient is V related to the Kolmogorov microscale. Let us write now not R, but Kolmogorov microscale substitute this V epsilon divided by epsilon, this gradient of V, and now take the square and multiply by nu. And this must be also epsilon, the energy dissipation rate. Now we have two expressions. One is from the spectral cascade, and the other is from the dissipation. And now, by combining those two, we'll be able to obtain all what we want. Now, just here we can, in this first expression of V sub R cubed divided by R, actually instead of R, we can put anything, including epsilon. So actually here we can put R equals epsilon. Not epsilon, eta. R equals eta. We can plug in over that because that Kolmogorov spectral flux, this is valid for any scale R, including the smallest scale what we have. All right, everything clear as well? So now we have, maybe it's better to write in the next page the same things over because we need a little more space to have. So we have V eta cubed divided by eta equals epsilon on the one hand, and on the other hand, we have V eta divided by eta squared multiplied by nu equals epsilon, two equalities. And now let us take this to square. V eta cubed 6 divided by eta squared equals E epsilon squared. And let us take this to cube, and then we obtain V eta 6 divided by eta to 6 and multiplied by nu to cube equals epsilon to cube. And now let us divide one with another. Then we have epsilon to fourth. V eta goes away. But we have still divided by a nu cubed. Equals 1 divided by epsilon, I guess. Am I right? So that kolmakorra microscale eta equals nu cubed divided by epsilon and to the power of 1/4. So, which means that if you take a stronger dissipation, more input, more energy input, more dissipation, then eta, the scale will go down, of course. So we might also want to have expression for velocity, kolmakorra microscale for velocity, for kolmakorra velocity microscale. Then we can take, for instance, this one over here. V eta is eta multiplied by epsilon to the power of 1/3, and eta multiplied by epsilon is going to be multiply this left and right by epsilon, and then we have here eta and v to cubed. So this equals to epsilon and nu, sorry, to the power of 3/4 and to the power of 1/3 equals eta nu to the power of 1/4. Now, velocity goes up with the scale epsilon. We have more input, velocity minus scale will grow. Length microscale will decrease, but velocity microscale will grow. And finally, we can also have characteristic time, tau microscale. Tau eta is eta divided by V eta, and equals. Now, this is the thing over that. Nu to the power of 3/4 divided by epsilon to 1/4 is eta, and 1 divided by V eta is 1 divided by epsilon and nu to the power of 1/4. And this thing here is going to be now epsilon to 1/2 and nu to the power of 1/2. So we have nu divided by epsilon and square root. All right. And that's more or less the closes the microscale thing. As you can see, microscale will depend on the energy dissipation rate type cycle. Now, how you feel about? All is clear? Arthur? And with that, we can go on. Now, what's next? I think we should now start discussing a little bit about particles with inertia in turbulence, and like also when I spoke about droplets, they are also like inertial particles in turbulence, and then we have oh well, wait, maybe before going that, we need to discuss a thing which is called Schmidt number. That is like we have different dimensionless parameters in the case of turbulence, and one is of course Reynolds number, like ratio again. This is basically that epsilon and new thing, and so the other one is so-called Schmidt number. The Schmidt number describes mass diffusion rate, which is basically the diffusivity nu, and molecular diffusivity. So when it might become important. Now let us have a look on this Kolmogorov turbulence thing. So what we have turbulent cascade. We have all different spectral components present in the motion in the inertial range. But if we go below the Kolmogorov microscale, then we have like a small velocity field. We have like a characteristic smallest characteristic scales are the microscales. Now,
one case, you mean continuous spectrum or
yeah, basically a continuous spectrum which gives rise to the fractal trajectories. You have like big loops, and inside the big loops, if you take, for instance, speak about streamlines of fluid, yeah, in the inertial range, you have all the scales present. So trajectory is fractal. It makes a big loop, and inside that big loop, we have smaller and smaller and smaller and smaller until the microscale. But if you go to below the microscale, then you will be having a small picture. So you take like big picture of the streamline, let us say, and then start zooming in. So as long as you don't resolve the microscale, you have like full nice fractal. So the curve is non-differentiable because you cannot take tangents anywhere because it's fractal. But once you reach the Kolmogorov microscale, then it becomes smooth, and below that Kolmogorov microscale, your trajectories become smooth, and at the end of the day, you can just see like a smooth curved trajectories. Now, what is the Schmidt number about? So what is now becomes important? How does this? What happens with diffusion of particles? You remember we started with actually with advective diffusion. And now it's like a time to recall what we had over there. And what we had is a so-called Peclet number. Peclet number, yeah.
Sorry, I'm not hearing anything. I'm still writing them.
Okay, so let us take a small break. Just tell me when you are ready.
So, microscale is the scale at which the fractal picture
disappears, and we have small,
streamlines,
and you will be seeing small streamlines.
Becomes small.
Yeah.
Because
And now, yeah, let us go back what we had with the turbulent diffusion. And if you remember, we had that thing which was called a Becquerel number. And Becquerel number measures the relative importance of advection as compared to diffusion. So we have now before we go, I need from here few formulas, and let me select and make copy them to the next page. So I'm going to take this sentence. Okay, I can take everything and then delete later on what is not needed. I go to the next page. That's what I wanted to copy from previous. And now a Becquerel number. Becquerel number was characteristic scale lambda multiplied by characteristic speed divided by molecular diffusion. Because, well, advective diffusion, I can say that the advective would be estimated as jump length, which is v divided by v multiplied by tau is a jump length squared. Jump length squared divided by characteristic time is the advective. But if we now keep in mind that that v times tau is lambda, so 1 v times tau gives us lambda, and then the other tau cancels away, remaining only 1 v. Then you can see that the advective is the lambda times v. And then we compare how important is this relative to the molecular diffusivity, and this gives us Becquerel number. Becquerel number is big, like we will be having a large gradient fronts and all that, which we have been seeing in those nice fractal pictures. On the other hand, if you have Becquerel number small, then it's basically only molecular diffusion, and we can forget about advection. Now, as you can see, what I need to have the product of the scale and the speed. And now let us take this characteristic, the Markov of microscale for length and for the velocity, and multiply them together. You can see that epsilon goes away from the product, and nu goes to the power 4/4, which is 1. So you can see that v eta multiplied by eta is just equal to the eta. And so Becquerel number here at the microscale, E at microscale, becomes equal to eta divided by diffusivity. And this is basically just the Schmidt number. I'm always a little bit having difficulties. We say this is a Schmidt number or 1 divided by this is Schmidt number. But well, it's a ratio to two things. Molecular diffusivity and viscosity.
Schmidt in the Deutsch, in the German way or English?
Yeah, I speak in German.
So SCHMIDT.
Yeah.
Okay.
Schmidt number, yeah.
It's the same guy of the orthonormalization of the base?
Probably not, because we like the turbulence thing.
Was much
Most likely no, but I'm not
Okay.
100% sure. Most likely. Now, what does it mean actually? It means that if you have that thing u divided by d, if this is big, then you have large Maclaurin numbers at the smallest microscale. So you zoom in, like you have some dye or whatever over there, or temperature at the smallest scale, and then you remember what we had at the large Maclaurin numbers. Now, at large scales, we have that turbulent spectrum, and also those pictures when you have the fractal flames like. But if you look at the smallest scale, then you have like those blobs, and then a lot of stripes. You remember those pictures with blobs, a lot of stripes. That's what happens if you have small velocity field and large Maclaurin numbers. So going back, when I started, we said that for passive scalars in turbulence, there are two different ranges, few important subcases. And one of those subcases was that passive scalars with big numbers in Kolmogorov turbulence, full spectrum of scales present. The other is passive scalars at small velocity fields, where velocity field has like more or less this characteristic characterized with a single scale. And in one case, you had fractal lines over there when it's Kolmogorov turbulence. In the other case, you had blobs and a lot of stripes. So the region where you have Lyapunov exponent with speed, where you have a lot of stretching. Material lines have lots of stretch. You have a lot of stripes with big fluctuations of, let's say, this temperature, a lot of temperature fluctuations over there. And then you have some places when you have blobs like temperatures like much less stretching, and you have regions which where the scale at which the temperature change is much bigger than over there. Surely you remember these pictures what I showed you. Not very sure about it.
Not which one. Like
I can
about many pictures.
do you remember the pictures? I can show. I can look for those pictures and show you. Let me show. Just to be sure. Let me show.
We have seen a lot of pictures.
Yeah, sure. That's true. That's true. Let me show you.
So the one in which, like, every time becomes half of the distance.
Now, now let me see at which place I can find those the easiest way. I can. Still probably from my folder over here. Too many files, but I don't remember also exactly the name, so it's better to look at everything. Well. Very too many. maybe here. I have a lot of slides when it might be, but I might have some. All right, one of those pictures is here. So I was speaking about that. This is now a really big picture. So this is something. Here also. Let me have a look. Yeah, sorry, but maybe you can. Small rest is not probably that bad for you as well. I don't know. Let us have a look what I have. Maybe that I can find also those pictures what I wanted to show. Different things. Yes, well, this is the stripe picture, and here, okay, I think we have both pictures what I wanted to show here. And now let me also share with the online guys.
May we have this file? Like
Sorry?
Complexity PDF. May we have it?
There are a lot of those things that are not really important for you, but I can give you if you want. All right. So here we have these are like old slides of mine. So but either way, in this picture here, what I was speaking about, if we have large Becquerel numbers and small velocity fields, then we have blobs. Now, blobs like here. Here are blobs, and then we have a region with a lot of stripes, narrow stripes. Narrow stripes are where we have had a lot of stretching, and so this tracer or temperature, whatever we have there, has been folded and stretched many times, and that's why you have many narrow stripes over there. And then we have those regions where almost constant density, where you just happen to have a very little amount of stretching, and that's why you have blobs. And now going back to, and here again, let us have a look on the other one. What we have, you also have seen quite many times this figure over here. This is when you have Kolmogorov spectrum, and then you have now completely differently looking picture. We have fractal isolines for the tracer, and just we don't resolve these Kolmogorov scales. Now, so regarding the Schmidt number, at large scale, if we speak about temperature, for instance, it doesn't matter Schmidt number, because in large scale it's exactly like in this figure over here. But it matters in small scales because now, depending on the ratio of the molecular diffusivity divided by the viscosity, if molecular diffusivity is bigger than the viscosity, then this means that the Becquerel number is small. Becquerel number at the microscale was, as we learned, was viscosity divided by diffusivity. And if viscosity divided by diffusivity is small, then we have small Becquerel numbers, which means you don't have this kind of pictures at this microscale. So suppose we look at the turbulence at Kolmogorov microscale. If we have viscosity divided by diffusivity big, then it's big Becquerel number at Kolmogorov microscale. And if you zoom in, you will be seeing something like that in this figure here. On the other hand, if it's the other way around, that the viscosity divided by diffusivity is small, then everything is small, like almost constant at this scale over here. So that's the difference. More or less clear? The Schmidt number, what does it mostly mean is that the differences become at Kolmogorov microscale. At Kolmogorov microscale, whether you have picture like this here, if it's temperature tracer, doesn't matter, a picture like that, a lot of stripes and blobs, then this corresponds to diffusivity being much smaller than the viscosity. And if it is other way around, you won't have this kind of picture over there at Kolmogorov microscale, where you have almost constant or like a gradient of density, and you won't have this kind of fluctuations over there. And actually, as a matter of fact, both cases are possible, and so this is an important parameter. Well, usually it is around unity, but it can be small, it can be bigger than unity, and quite significant. Like if you take heavy molecules, like what it actually is now, it's a good idea to think about from the molecular consideration. What are the maybe I should take a picture just to keep this track in the screen as well. Maybe I just copy from here to the screens because it's better to have. No, I cannot. Okay, I understand. Let me copy from here to the screens. Oh, this was all. Now, this is what we have at small scales. And then let us also take a picture from the previous slide. Oh. Computer again became a little bit slow. I'm taking a copy, and now I need to wait. I hope now it appears. Yeah, now it appeared. All right, let's make it a little bit smaller. This one over here. All right, and now let me share again these screens over here. Now, with that, I think we're more or less done with the Schmidt number. So Schmidt number is right. Yeah, I wanted to a little bit talk about the possibility why we can have small and big Schmidt numbers. The reason is that both viscosity and diffusivity, they are estimated as in the same way as characteristic scale squared divided by characteristic time. They are both estimated like that. Nu is like that, and D is like that. But the thing is, which scale goes to what? Now, if we speak about the diffusivity, then this basically viscosity is basically momentum diffusivity. How far momentum is carried? Because viscosity describes the force which acts between layers which move with different speed. And why you have that is that if we have one layer going that way and the other going that way, there are molecules which diffuse from one layer to the other. So a molecule which goes from here to here, then it comes with momentum that way, and now it must obtain the momentum of that way. So it transfers momentum. So because of that, here we need to write the characteristic scale of the molecules of the medium. So of molecules, medium. Where the scale characteristic space scale and time scale of the molecules of the medium. On the other hand, if we speak about diffusivity, then we can have actually big molecules. And if we have big molecules, which is diffusing, and we have small molecules, which are the fluid molecules over here. So fluid molecules have like much more mobile because they are small. They have say mean free path, but this big molecule here gets hit many times with the small molecule. So the mean free path for that big molecule is much smaller. So usually, if we have big molecules, we expect this diffusivity can be much smaller than the diffusivity for the molecules of liquid. Now, on the other hand, if we speak about diffusivity for temperature, so diffusivity for temperature, what temperature is? It's heat. Heat is a kinetic energy. So if nu is a diffusivity momentum, for temperature diffusivity is the diffusivity of temperature of energy, of the energy of a molecule. So these two things are of the same order of magnitude because they are both the diffusivity of the molecules of the fluids, of the medium. So you would expect usually the Schmidt number for temperature to be around unity. But if we speak about admixtures like dye, if you have big dye molecules, you can have actually very big Becquerel number small scales because molecular diffusivity, the scales go down because you have big molecules of the dye. All right?
Like the fact that the viscosity is the linear momentum diffusivity. Okay, like I can follow it like this.
Okay, so temperature is the same because temperature is the diffusivity for energy, kinetic energy of the molecule. So for temperature, it is the same. So because of that, if we speak about Schmidt number for temperature, so Schmidt number can describe any diffusion process. It can describe the diffusion of dye molecules, but it can also describe diffusion of the temperature because also actually the same thing, all what is the same equation describes temperature and the dye concentration. And so if we speak about the advective diffusion of temperature in the turbulent fluid, then the Schmidt number comes down to the ratio of the diffusivity of momentum and diffusivity of the energy. But these are usually of the same order of magnitude because they are both due to the motion of the molecules of the fluid. Okay, so the conclusion is that if we speak about temperature, the Schmidt number is around unity because they are both very similar diffusivities, the diffusivity of the molecules of the liquid. On the other hand, if we have the diffusivity of a dye molecules, like are often organic molecules, which are really big. If we speak about water, H2O, these are fairly small molecules. But if we speak about dyes, they are organic molecules can be very big. And in that case, diffusivity as being estimated as scale squared divided by time, then the scales becomes very small and diffusivity becomes very small if we have big molecules. So for organic molecules, usually you have diffusivity much smaller than viscosity. So that at small scale you have big Becquerel numbers. So stripe pictures what we have showed over there for temperature for dye. All right. Now it's okay.
Yeah, it's like difficult to digest for me. It's not a small thing, I guess. I'm not sure, like as a model, like saying, seeing like viscosity, as the linear momentum diffusivity, it's not that trivial, I would say.
Right, but yeah, we could discuss it more in more details, but actually we are also running out of time. So we have today, we have half an hour left and then it's only one more lecture. So my plan for next lecture was very briefly to describe things what I myself a little bit not so good, but still I think it's quite somewhat important. So I will be trying doing it. So this is like a weak turbulence, which we slightly mentioned in the introduction. Like it is a 4-wave processes, 3-wave processes. Like how to describe, for instance, waves in the sea, how they interact and what will happen with them, like wave turbulence. That's a plan for the next lecture. So this very briefly, this could be done much longer, but just to you get a rough idea what is going on there. So that's a plan for next time. So this time we would like to finish with this thing here, and there is one more thing what I wanted to show you actually in this regard. So once I finish with that Schmidt number, now yeah, let us just because I'm always a little bit inconvenient. Which divided by which? Is it the molecular diffusivity divided by molecular or the other way around? Let us check. Schmidt number. You know, for me, like you know the thing, but if even if I had like before lecture check it either way, I'm sorry. So as you can see, it is diffusivity divided by viscosity divided by diffusivity. So a big Schmidt number means big Becquerel number at small scales. So you would expect big Schmidt numbers at if you have dye molecules, heavy dye, which have slow molecular diffusivity. A big Schmidt numbers, which basically means a big Becquerel number at the microscale. All right. Now, the final topic for today, what was planned, was particles with inertia, and this is not going to be too difficult. This is not going to be too difficult. So what we'll be doing now is to studying how we'll move particles with inertia in fluid. So at the microscale, again, we speak about microscales. At microscale and at small sub-microscale, even smaller than the microscale. And then we have basically vicious drag because there is no turbulence by definition below microscale. And so we can, for small particles, we can use the Stokes formula, something like, now again, writing from head, it's something that would be like 6 pi eta, like you have viscosity, which is 2 versions. One is divided by density, and the other is not divided by density. I think this is cell which is not divided by density. And then we have a radius, and that's it probably. Stokes drag.
I wonder, wasn't
yeah, here we need to have dynamic, only is dynamic. Yeah. Here you need to, because force is has kilograms times meters per second square. We need to have kilograms here, so this is not divided. It's just normal viscosity, not dynamic viscosity. So Stokes drag, and then let us consider things in co-moving frame. Yes.
Sorry, normally you mean kinematic.
Yeah, kinematic. Yeah, dynamic kinematic. I think is it the dynamic. Which way? Kinematic is probably divided, and dynamic is not divided. I think that way. Kinematic shouldn't have. Yeah. And then let us go to co-moving frame. Let us go to co-moving frame. So this actually becomes now force of inertia. And so sorry, and relative velocity is also here. So a little bit like one term is velocity, relative velocity.
Sorry, Stokes die. What?
Drag.
Drag. Okay.
Yeah. And now if we have a water parcel moving with certain acceleration a, then this here is minus m times v of the particle. Now this is v related. Speed of particle relating to the fluid, and here is speed of the fluid. So VR is v particle minus v fluid. And here we have dot. And now we assume actually this here to be small. So we have a light particle which almost moves with the fluid, but slightly deviates because of this Stokes drag. So we assume that the speed difference Vp minus V is small. And so the relative, because of that, we can write V relative is minus mv dot, and divided by 6 pi eta r. That's it, I guess. Which means that V of the particle is V of the fluid minus that guy over there, minus mv dot divided by 6 pi eta and r. And now, what is V dot? V dot actually we can we can use now the Newton's second law of fluid in terms of Navier-Stokes. We have rho dV over dt, which is exactly what we need to have over here, is as long as we neglect the viscosity, and then we have plus gradient of P equal to 0. So that V dot what we need is minus gradient of P divided by rho. And now let us plug in here. We obtain now this as D minus, probably plus because we have minus minus, and M gradient of P divided by 6 pi eta rho and R. We have here small certain parameter, and we have this is constant, and we have here gradient of P. Now, let us recall when we spoke about basis scalar turbulence. So there is another thing. So we had classification. We had the two figures what I showed you before, like small scale, large scale, below Kolmogorov microscale, above Kolmogorov microscale. But we had also particles die in compressible fluids. And then I said, that what is compressibility? Compressibility is the ratio of the compressible part, which is called potential part, and the sum of the solenoidal and potential part. Do you remember something? Maybe. Okay. Once again, compressibility. Compressibility C. Compressibility. This was defined so that if V is equal to certain curve of A, which is incompressible part, plus certain potential part gradient of phi, and then compressibility C was the relative importance of the potential or compressible part. So this guy over here is the compressible part. The relative importance of the compressible part. So C was by definition something like squared mean value of gradient of phi, compressible part, divided by the sum of the both. Gradient of phi squared average plus curl of H squared average. This was compressibility. And then the conclusion was that if we have big compressibility, then particles start gathering into patches. You remember I showed you pictures of the particles floating on the fluid surface and then started to gathering in patches. Or which is the same if you are on a boat and look at foam floating on all the surface, it starts also gathering into patches. Because if you have compressibility, then this gives rise to patchiness, so to say. Because particles mostly get stuck into convergent parts of the flow. Flow comes in, as it keeps them trapped over there. And if we average over the trajectories, the average divergence of the velocity field becomes negative. Even if you average over the space, the average divergence is 0. If we average over the trajectories of the particle, it becomes negative. And now have a look on this expression, what we have for the particle, inertial particle in fluid. This V over here, by assumption, assumes that the flow is incompressible. So this is incompressible. Incompressible. By our assumption. But this thing here is exactly the potential part. Potential. So just we automatically obtained a so-called Helmholtz decomposition. Helmholtz decomposition is just separating the potential part and solenoidal part and potential part. So we actually obtained automatically here the Helmholtz decomposition. So we have a compressible or solenoidal part, and we have a compressible or the potential part. And which means that if we have inertial particles in fluid, they start gathering into patches. Right? This is the conclusion. And actually, this is something which you can easily notice by yourself. If you take a cup of tea, for instance, and put sugar into tea, and then mix it, then what happens with sugar? It starts collecting into the center. Is that true? Yeah. And that's exactly what is going on in action. Sugar particles are inertial particles, and they start gathering into the center because exactly of that effect.
But that's not just the pressure.
Ah, sorry?
Not sure. Like, it doesn't have anything to do with the fact that when I rotate, the profile of the water becomes a parabola?
No.
Okay.
If we speak about sugar, I can make another big picture here also. So you have a cup of tea, and then you rotate it. So basically, water goes like, no, this maybe was not very successful figure, but let me tell you. So here is a cup, and then water goes from us here and comes toward us here. So like you put the spoon it into motion. And then how the water starts moving is that you have, apart from the horizontal motion, it starts also having vertical motion. And vertical motion is like that. All right? And then now, like cell like that. And then, which means that if we have here sugar particles, and they start going together with this convergent here, we have at this surface, we have convergent flow, and these particles start going over there. Something like that. Yeah, maybe it's not 100% that thing because we have here like also compressibility of the flow coming also from the facts that they are stuck to the wall. So it's to be 100% honest, this is not exactly because of inertia, but with inertia gives still rise to exactly the same thing. So because you can see that inertia will give you potential part of the flow, potential component to the velocity field. So inertia is what starts making particles into gathering into wedges. So if you have dust in a turbulent airflow, these dust particles, they are not just randomly placed in the space homogeneously, but they, because of if they are big enough, they have inertia big enough, they start gathering into patches. Like as forms of dust particles, not homogeneous distributed, because of this effect. Yes.
So the point in which everything gathers is the point of minimum of the scalar potential?
No.
Like
no. Yes. Here, yeah. Yes. Right. Yeah. You're actually right. Yeah. Because actually, if we have in extreme case, if you take extreme case of when you don't have an incompressible part and you have only a potential part, then you would also be able to describe this in terms of actually potential energy indeed. So let me see.
Sorry, and the last thing, like in the last slide, like so yeah. The incompressibility, it's the first term plus the
compressibility is C, and this definition is given in the red.
But it's reconducted like to the first term plus all that part on the down left, on the bottom left, and then the potential part is only the gradient of the pressure.
This is potential part. This is solenoidal part.
Yeah, that is clear. But like here, like the incompressibility
Yeah,
is all
yeah.
this stuff, and the
Yeah,
potential
yeah.
only the gradient of pressure.
Yeah. So this here is potential part. This is solenoidal part because we did assume that the velocity field itself is incompressible. This was our potential. So we have water which is incompressible. The velocity field of water, this is incompressible. This is solenoidal.
So only this one, like this line is not saying this stuff is incompressible.
Incompressible is only that.
Okay, this line doesn't matter.
This line doesn't matter.
Okay, okay.
Sorry about that line. I'm explaining I should use laser pointer, but sometimes I use pencil and then the lines happens.
Okay, no, because we're looking like the two of them. Okay, okay.
Yes.
Thank you.
But you are right when saying that it has to do with the potential energy. So if we speak about like overdamped motion of particles, you have that mobility thing. Like if you have Brownian particles, drag force is mobility multiplied by speed, and then if we have a potential landscape, let us say that if on the other hand, on the one hand, a force is a drag force multiplied by drag force is velocity multiplied by mobility on the one hand. On the other hand, this equals to gradient of potential energy phi and a minus gradient. And then you can say that here we have a velocity field for the particle, which is minus gradient of phi divided by b. But then we have also, apart from that f, we have also diffusivity d, which describes the diffusion of Brownian particles. And then we can have, we'll be having, if we have phi itself, if phi is a certain function of coordinates, like random function maybe, or maybe not that random, maybe some sinusoids or whatever. Like if you have like matter, crystal matter, then you have also a certain potential maybe as for electrons moving there, or maybe some holes if you want to a semiconductor or something like that. Then phi is a potential energy for these particles moving in the semiconductor. And mobility, so mobility you can express the velocity of these particles in this medium. And then we have the same thing that we have the motion of the particle has on the one hand, you have velocity phi, and also v, on the other hand, you have diffusivity d, so that you can for concentration particle, where you can write the same thing, plus v gradient of n and equals to d Laplace of n. But we have ancient relationship between mobility and d. Diffusivity and mobility, these are related to the ancient relationship. And then when we all do that, then we know what we must have at the end of the day is Boltzmann distribution. That at stationary state, when considering together that v and that d, you need to have n proportional to E minus phi potential energy divided by k with t. So you also see that you need to have patchiness. All the particles will gather into points where you have the minima of potential energy. So actually, these two things are indeed, as Enrico said, this is completely true. And actually, this thing that in potential fields you have gathering into patches, you can also look at this in terms of Boltzmann distribution and minima of potential energy. But of course, things become a little bit more complicated if that phi itself here is fluctuating in time. Then it just won't manage to reach the minimum because it's just minimum disappears before it is reached. But still, the same remains valid. They are still gathering into patches. Yeah, still gathering information. Well, this is what we did discuss before when we spoke about compressible velocity fields. And the main lesson actually here, what we had was that inertial particles in fluid will have compressible component here. Oh, sorry. I wanted to take laser. So they will have a compressible part potential part in the velocity, effective velocity field. So velocity of the inertial particles in fluid is the incompressible velocity field of the fluid which is moving, plus potential part which makes the inertial particles going into batches. Now, how is that? More or less okay, Arthur? Right on. All right, and then with that, indeed, as planned, we have gone through those topics what I plan to have with you, except for the 3 and 4 wave turbulence and things like that, which we will leave for the next lecture, the next and last lecture. All right. So, any questions? Arthur?
No, I don't think so at the moment.
Sorry, once again?
I don't think so at the moment.
Yeah, all more or less clear?
Yes.
Raido?
No questions right now.
Mm-hmm. Yeah, regarding exam. So I think Raido has been sending me quite regularly homeworks. So, but now actually, will you be working together with the lecture notes, or did you decide to collaborate?
Yeah, I'm going on. Then I will have to figure out how to split the work.
Yeah, I wonder, Arthur, actually, I think the proposal would be valid for you as well, that if you, instead of submitting the homeworks and doing those things, to join them together to like make a good lecture note material in Overleaf, then you would be also probably welcome to join, right? Because there's a lot of things actually to write down, and with 3 people, it would be probably easier. Yeah.
In that situation,
so just tell us what you would prefer, rather going the way of submitting homeworks and having a discussion later, or joining these 2 guys working on the lecture notes on our list, and having like exam would be the project of having turbulence mixing lecture notes at the end, somewhere in January. Your mic is muted, yeah.
I don't know. Yeah.
But you can probably take your time. I can send you an invitation of the Overleaf project. You can take your time and think about it, which one you would prefer. You can have a look what they already have there. They have started doing it. And the deadline would be, like in our case, I think the deadline for putting marks into the system is somewhere around 20th of January, right? Was it? Yeah, around that. So it would be okay if you finish working on these lecture notes by 20th of January, around.
Professor, actually, I was thinking about bringing the project more far in of that. Until that, I guess that some chapters would be ready for evaluation.
Yeah.
But just I don't want to write them fast and
yeah. Okay, that's fine. That's fine. You can continue. You're very welcome to continue later on. But yeah, to have something for exam, to ready by that time, and so
there are a lot of missing things that I would like to explain, like so that someone that is coming from any field, from physics, mathematics, or engineering, can follow all the path through until these complicated things. And also because that I've seen that like there is a lot of intuition in these lectures, but as I told you already, like I was trying to explain why intermittency and the plot of the like distribution of probability are correlated into turbulent fluid, and actually I was not able to prove that. Just I was able to give like an idea, but I would say also the listener was not very like open to intuition, waiting for a proof, but
Yeah.
as mathematician does. But
Yeah.
I was not able to do that.
Yeah. So to sum up, that something ready by 20th of January for exam, and then you can continue and improve later on. We would very welcome it. So, and at some point, if I have some time, I would be also looking on what we have and maybe improve. And next year it would be much better than everything. But yeah, if you feel like doing it the other way, like submitting homework, is also, of course, very good choice, because in that way you will be perhaps. The difficult is the thing, which is better, because if you write notes, then you also learn. Like the aim is to have you understand as well as possible things what I have done here. So one way is like solving the exercises. The other way is doing this this project and writing selection of both serve the same purpose. And so so just it comes down to what you would prefer yourself. So this like a one time off, and the next students already want to be having that, but this time, because we don't have it yet, so there is this offer is on table. All right, but Artur, you can take your time to decide. Oh, what I was actually planning to do, I can show you over the screen sharing what they have done. So let me see. Where is the project?
I guess I made some changes.
Yeah. Let me see if I need to open the right one. I have many overview projects here ongoing, but let me see if this. I can share my screen already. No, let us see if it's, for some reason it's still loading it. Yeah, now. No, this is not set. That's set thing. Why did it's this one probably? Yeah, that one. So it looks like that. So they have written here some different tech files over there, and the compiled thing is over here. So if I can share with you the same project, then you can arbitrary number of people can work simultaneously, actually, as long as they don't know the editing exactly the same thing, in which case it might become messy, because you write type and the other type deletes just what you wrote, and then that's probably not a good idea. But if you write in different places of the file or different files, that's fine. You can write simultaneously. And then you have automatically compilation on the right window. So you can just, if you make up your mind right now, tell now. Otherwise, you can take your time to decide.
Did you do the main? The main file. Main.txt. No. I never called the one main.
So
Artur, have you written things in LaTeX?
Yes. So
That's no problem then.
So okay. Let me try to recap. So the choice is between working on the lecture notes and trying to finish that before the 20th of January.
Well, as Enrico here said, that maybe not finish, but have big enough pieces what you yourself feel about more or less happy, that I can see the result. Like if you or different people work here. You just one Enrico says that okay, I did that. The other Enrico says that okay, I did that, and Jarko says that I did that. If it's enough volume, then I can say okay, that's fine. You all get good marks.
I would like also to make a cross check with the others so that we improve our.
So not necessarily everything finished by 20th of January, but like a reasonable amount, like what you would expect from the work amount equivalent to what you would normally expect from a course with 6 credit points. You more or less know. I think everyone more or less knows what is a reasonable amount of work. I don't need to exactly calculate now hours because you have been studying in university for a long while and you know what is a reasonable amount.
I guess we will work on this more than the number of hours from the credits. The point is that like until the 20th of January, the version that would be come out from there would not be the level that I expect to be done when I will finish this. So I mean, I don't totally care about the grade, but I hope that like there will be like an inclusion of the future work of the 20th January in the middle of all the exams. Then I can't put on this and very debug or the lectures that we did because some kind of debugging.
So Artur.
And the other option is to make the homework and write them out nicely and have a discussion about that. Right. So
the other option, you submit homeworks. If there are some homeworks which you feel you cannot do it, you can skip those, but at least the majority of the homeworks are done. And then we make a meeting over Zoom, and then I ask you, like give you a small like oral exam. I ask you few questions. I am not going to give you difficult problems, but just to see if you have more or less have know the things. Like I am not going to ask you all derivations, but like the basic concepts like what happened. Probably I'll but it will be something like I give you each. We had 16 lectures, and each lecture has certain topic. So I would be asking, like, let us take this lecture. What I give, and not number of lecture number, but the topic of the lecture. The topic is a lecture with the topic of, let us say, compressible body tracer advective diffusion of passive scalars in compressible velocity fields. Let us say this is a topic. And then your task would be answer me. I give you some preparation time, and then you prepare on your paper, and then show me over the screen what you wrote on the sheet, and then explain what is your understanding of that, and then the grade would be based on your submitted homeworks plus the answer what you give during that oral exam. That is the alternative.
Okay. I think working on lecture notes is a fun idea, basically because I've never done an exam type thing or grading like that before, so that's different. So I think I like that option, working on the lecture notes.
No, one second, which one? Lecture notes or exam?
Lecture notes. Lecture
notes. Okay. Then I'll invite you also. I send you invitation. I think I have your email. I'll send you invitation to the Overleaf project.
Okay.
All right. Good. Yeah, probably I can already. Okay, I'll do it a little bit later, but I'll do it soon. All right, and with that we are indeed finished for today. So then, bye until the next and last lecture.
Yeah, I have one question also more.
Yes.
So where when we can do this exam, or we just privately send some emails and
we just privately we can agree which is a suitable time.
Yeah.
We have not so many participants, so probably there are some other guys who have been like quietly following the YouTube recordings, because I don't know about them. We might have a little bit more than the 4 of you, but either way the number is not so big, so that so can just can privately agree on the time.
Okay.
All right. So then, all the best until next week.
Bye.
Bye.
Bye.